Okay, so what's up mga ka-ChE? It's Kuya Dale here. So I'm back with another checkout lesson, and today, so this lesson will be the last lesson for the basics of the chemical engineering calculations, which we'll find out later. So before we will go there, so shout out muna, okay? Shout out muna sa mga solid sharers namin sa FB, such as sila ni JM, nila ni Jurgen, ng Crystal Jane, Kenneth James, Francine Norvik, sila ni Rix, Shelo, Vanessa, sila ni Deha, Sayura, and then shout out din for our teachers in QRC, especially kang Ma'am Lara, Sir Lowen, and Ma'am Mitch. So thank you. Salamat po sa pag-share ng aming video. And lastly, may special shoutout ko later kasi may nagturo sa akin kung paano yung shortcut sa pag-convert ng heat capacity units. We will go there muna. Okay, so special shoutout to Sir Conrad Monterola of Malayan Colleges Laguna. He's also my teacher in QRC, and especially in the unit operation. So he taught, it gave me an idea on how to solve this shortcut. So sabi niya, so why wouldn't you use, so di ba R lang yan, 8.314 at saka 1.986. So ayun ang sinabi niya. So tinry ko at nakuha ko. Okay, so I will give an example. So sample problem for that. Okay, so the heat capacity of sulfuric acid in a handbook has the units of joules per gram mole per degree Celsius, and is given by the relation here 139.1 plus 1.156 T. So this T is in degrees Celsius, and you have to modify the formula so that the resulting expression leads the heat capacity with the associated units of BTU per pound mole per Rankine, degrees Rankine, and with T in degrees Rankine. Okay, so let's just write the expression first. So Cp is equal to 139.1 plus 0.156 T degrees Celsius. So the units of these is joules per gram mole per degree Celsius. So gamitin natin yung shortcut ni Sir Conrad. Okay, so we'll have to divide it by 8.314 joules per gram mole Kelvin. Remember that degrees Celsius here is in unit temperature difference, so it does not matter if it is in degrees Celsius and or in degrees in Kelvin, because they have the same unit difference of 1. Okay, and then we have to multiply it by 1.986. Then the units will be BTU per LB mole per Rankine. Okay, so as you can see, if you multiply that, the resulting expression will be 33.23 plus 0.0373 TC. Okay, and that has the units now of BTU per LB mole per degrees Rankine. Okay, and then we have to convert this degree Celsius to degrees Rankine, right? So one way we can do that is that the PR is equal to 1.8 times the temperature in degrees Celsius plus 32. So this will be in Fahrenheit now. And then we'll have to add 460. So transposing all these values to the other side so that we will be left with degrees Rankine. So the degrees Celsius now will become degrees Rankine minus 492, then divide it by 1.8. Okay, so that will be that. And then substitute this there, substitute this there, and you will get the final expression to be 23.04 plus 0.027, and then yeah, it has the units now of BTU per LB mole per degrees Rankine. Okay, so that's it. Okay, perfect. So I haven't explained to you why 1.8 and 1. Okay, I have said in the previous video that 1.8 degrees Fahrenheit is equal to 1 degrees Celsius, or this actually 1 degrees Celsius, and then it is equal to Kelvin, diba? So I haven't told you that. It's because I forgot the last time. So I will explain to you now. So notice here in the right side, so this is in Kelvin and this is the other side is in Celsius. Okay, so the base point or the basis of their interval is the boiling point of water, which is 100 degrees Celsius. Okay, and 100 degrees Celsius is 373 Kelvin and 672 degrees Rankine and 212 degrees Fahrenheit. So if you get the range now, so the freezing point of water is 0, okay, in 0 degrees Celsius, and then the boiling point of water is 100. So the interval or the range of that is 100, and it is also the same in Kelvin. So the difference, okay, so the difference in Kelvin is equal to the difference in degrees Celsius. Okay, so it's just 100, they're equal. And also if you go here in the left side in the Fahrenheit and the Rankine, the range now it will be 180. Okay, so if you get the ratio now, of the ranges 180 degrees Fahrenheit. If you want to get the equivalent of that in degrees Celsius, so this is in also difference. Okay, so just divide both sides by 100. Okay, so if we divide this by 100, it will become 1.8. So this now is the reason for the relation na 1.8 multiply sa range ng Fahrenheit, and then 1 will be multiplied by on the range of degrees Celsius. Okay, so this is also true with with degrees Rankine. So that's why we have this relation also. Okay, so that's that. So now we'll go to the actual lesson, which is the pressure and static head. So do you feel any pressure right now? Okay, so no, I don't feel any pressure right now. Diba? So kayo nang maghanap mo sino yan. I'm sure you remember who she is. So definition of terms na tayo. Pressure is defined as the normal or perpendicular force per unit area. So as you can see here, the the pressure or the force is applied perpendicular to the unit area. Okay, meaning is 90 degrees. It's 90 degrees with respect to the surface. Okay, so there are two here. There are two pressures that are acting in this cylinder. So we have the atmospheric pressure, which in if you are in the sea level, you have 1 atm, and then if you have a liquid here, you have the for example mercury. So it will also contribute a pressure on its own. So if you add that, so the total pressure now will be named as the absolute pressure, and then it will be from the mercury, contributed by the mercury, and then contributed by the atmosphere. Okay, so here are also different units for pressure. So we have bar, we have kilopascals, we have torr, millimeters mercury, inches mercury, feet water, inches water, and then psi. So don't be confused by Hg and H2O. It's just that the fluid that was used in the manometer or the pressure gauge is mercury or water. Okay, so it really differs on the liquid that was used to measure the pressure. So later we will explore that. Okay, and then we have here conversion factors. So you cannot memorize this. So in your Paris, this is located in table 1-7. 1-7. Okay, so you find that there. So some add-ons. So pressure and temperature can be expressed in either absolute or in PSIA, pounds per square inch, absolute, or relative scales. So rather than using the word relative, the relative pressure is usually called gauge pressure or PSIG, or pounds per square inch gauge. So the atmospheric pressure is nothing more than the barometric pressure. So the relationship between gauge and absolute pressure is given by the following expression. So absolute is equal to the gauge plus the atmospheric. So that's what I have explained earlier. So another term which you should become familiar is vacuum. So vacuum, when you measure the pressure in inches of mercury vacuum, you are reversing the direction of measurement from the reference pressure, so the atmospheric pressure, and toward zero absolute pressure. That is, vacuum is equal to atmospheric minus the absolute. Okay, so that's that. So let's go to the sample problems directly. So so that we can see the applications of this. Okay, so the pressure gauge on a tank of carbon dioxide used to fill soda water bottles reads 51 psi. 51 psi. At the same time, the barometer reads 28.0 inches mercury. So what is the absolute pressure in the tank in PSIA? So don't be afraid of inches mercury and PSI. Okay, so they're just really simple units. Okay, so as you can see here in the gauge, the pressure gauge, we read 51 psi. So as you can see, this is gauge, right? Because you have no the atmospheric pressure cannot affect the pressure of the carbon dioxide inside the tank. You have to assume that the tank is rigid, so it cannot be deformed. Okay, so the atmospheric pressure has no contribution to the total pressure of the carbon dioxide inside. That's why we have to for us to get the absolute pressure, we have to get the barometric pressure. So this is the barometric pressure measures the pressure of the atmosphere. So we are tasked to find the absolute pressure in the tank in PSIA. So we have now the 51 psi. So we will not convert that anymore. So P absolute is equal to 51 psi G, so this is in gauge, plus the 28.0 inch mercury. Okay, so the conversion of that, as I have shown you in the previous slide, is 29.92 inch mercury, and then convert that to PSIA, have to multiply it by 14.7. Okay, so 14.7, and then you will get the absolute pressure of 64.8 PSIA. Okay, so it's not absolute because we have accounted for the barometric pressure. Next, so small animals such as mice can live at reduced pressures down to 20 ppi absolute, so although not comfortably. So in a test, a mercury manometer attached to a tank as shown in the figure reads 64.5 centimeters mercury, and the barometer reads 100 ppa. So will the mice survive? So we have the standard of 20 ppa absolute, so we have to calculate if the mice can survive in the new conditions that we have here now. So question, will we add the pressure or will we minus? So as you can see here, there is convention actually. So if the if you take your reference point, so for example right, so it's in the right, so it is lower than here in the left, so meaning the pressure, the atmospheric pressure is higher than the pressure inside. Okay, so it is higher than the pressure inside because this is open to the atmosphere. So what does that tell us? It tells us that the conditions inside the container that contains the mice is in vacuum. All right, so because it is if it is equal, so there will be no height difference in the liquid here. But we have, okay, it shows us that the pressure outside is greater than the pressure inside, so this is in vacuum. So we have to calculate for the absolute pressure. So as you can remember in the previous slide, I have shown you the formula. So PATM minus the P vacuum. Okay, so it will be now easier to calculate. Minus, we have 64.5 centimeters mercury, so it's centimeters mercury, right? So what we are familiar with is the millimeters mercury. So if we convert the millimeters to centimeters, we just have to divide it by 10. So 101.325 kPa, and then it will be divided by 76 cmHg. So that's actually it. And then the answer will be, so the answer will be 14 kPa absolute. Okay, so conclusion, the mice will not eat. Okay, so last topic that I will share with you is the pressure difference. So in the chemical engineering calculations, you will be facing these kinds of calculations. So we have here an orifice. One way of getting the velocity of the fluid inside is through a pressure difference. Okay, and also there are also applications for this that uses pressure difference. Okay, so here the pressure is higher because the fluid occupies the size all of the area of the pipe. Okay, so that will be, that's why it will be greater. Okay, so as you can see here in the manometer, so it pushes on the manometer, and then the liquid level here is lower than the liquid level on the right. As you can see here, there will be a pressure drop because the flow of liquid is restricted. So it will not be as strong here in the pressure here, as strong in the left. So there will be a pressure drop. So that's what we will be calculating in these scenarios. So if we zoom in to that here in the left, so we have the pressure right here, the pressure contributed by the part liquid here. This is the same liquid. So pressure here, let's say this is water. So the water, let's say this is water. So the water contributes for the pressure in P1 and also in P2. Okay, so here it pushes on our liquid, and the liquid here in our manometer, and then also in the other side it also pushes on the liquid, but not as strong as on the left. So if we get the formula on how do we solve this for our pressure difference, so we have to have this division. Okay, so this will be the equal sign for us to calculate the net pressure on this setup. Okay, so starting here in the left, so we have P1, and then we have to add the pressure. This is the P1, right? And then we have to calculate its contribution here, right? So we have to calculate its contribution there. So we have our row 1. So let us say that there are 3 fluids here that distinct so from one another. So fluid 1, fluid 2, fluid 3. So how we can get the pressure difference there? So in the left side we have to add. Okay, so rho G D1, that. Okay, and then we have to add also the contributions of the pressures on that left right side. So we have P2, and then we have the contribution of this pressure of the fluid here and also this fluid here. So we have P2, and then we have our rho 2 GD2. So that's this liquid, and then for this liquid rho 3 GD3. Okay, so that's just that. So assuming that the pressure, the liquid is the same. Okay, so which is also the case of usually the case of many setups like here. For example, this is water. So the density of liquid in the left side is equal to the density in the right side, meaning the liquid is the fluid is incompressible. So we now have the simplification that our rho 1 is equal to our rho 3, right? So because this is just the same here and then here, these are just the same, so we'll just rename that with rho without any subscripts. And then we know that D1 is also the sum of D3 and D2, so we can simplify it further. D3 plus D2, right? As you can see here. So we will move this to the left side, so that we will have the P2 will move it to the left side and the rho GD1 will move it to the right side, so that we will have the simplification of this formula. So we will substitute the D1 first. Okay, we will substitute the D1 first. So P1 plus rho G D3 plus D2, and then P2 rho G D2 plus rho. If you distribute it here, so rho G D3 and rho G D2, and then if you move that to the right side. So if you distribute the rho g here, so the rho GD3 cancels, okay? So this term and that term cancels. So P1, we'll now have to simplify this P1, P2, and then move that to the right. We will have the P2 GD2 minus rho GD2. So to simplify it further, P1 minus P2 is equal to rho 2 minus rho times GD2. Okay, so that's the simplified formula for that. And then let's move on to the last sample problem. So in measuring the flow of the fluid in the pipeline through an orifice shown in the figure, so with the manometer used to determine the pressure difference across the orifice plate, the flow rate can be calibrated with the observed pressure drop or difference. So calculate the pressure drop, so P1 minus P2 in pascals for the steady manometer reading in the figure. Okay, so we'll just apply the formula directly. So rho 2 minus rho G D2, or it's just D now. So D. So we have the rho 2, which is the fluid in our manometer, which is 1100. And then we have the density of our water, which is 1000. So this is in kilograms per cubic meter. And then we have our G, which is the acceleration due to gravity, is equal to 9.81 meters per square second. And then we have our pressure drop or difference, which is 32 minus 10 millimeters, which is equal to 22 millimeters. Or if we convert it to meters, 0.022 meter. And then we will get the difference, pressure difference now as 21.6 pascals. Okay, so that's it. Now I will give you the sample problem. So this are really easy. Some practice problems. You can do this on your own, okay? And then I would like to see your answers in the comments, okay? So number 2 is really similar to what we have just done the problem, okay? And then number 1 is just conversion, okay? So that's it for our last lecture for the basics of chemical engineering. So still the reference will be Himmelblau and Riggs. And then if you have any questions, just contact me through my Facebook account in the description. Okay, so don't forget to like this video and subscribe to our channel. So that's it for our last lecture. Merry Christmas and enjoy your Noche Buena in the 24th. Okay, so bye-bye.